You think the sun is eternal, a constant source of light and warmth, rising every morning, setting every evening, reliable, permanent. But it's not. The sun is dying, slowly, inevitably. And when it dies, it will destroy Earth. Not might, will. This is not speculation. This is stellar physics. The sun is a middle-aged star, about 4.6 billion years old. It has about 5 billion years left. And in those final years, it will swell into a red giant, growing hundreds of times larger, hot enough to vaporize the inner planets. Mercury will be consumed. Venus will be consumed. And Earth, if it survives at all, will be a scorched, lifeless rock. But long before that, long before the sun becomes a red giant, Earth will become uninhabitable. The sun is getting brighter. Right now, every year, in about 1 billion years, the increased luminosity will trigger a runaway greenhouse effect. The oceans will boil, the atmosphere will be lost to space, all life will end, Earth will become Venus, a hellish hothouse, and there's nothing we can do to stop it. I'm Leonard Susskind, and I've spent 50 years thinking about physics and cosmology, and I'm going to tell you why the sun will destroy the Earth, not as a possibility, as a certainty, written in the laws of stellar evolution. Let me start with how the sun works. The sun is a massive ball of hydrogen, about 73% hydrogen by mass, 25% helium, 2% heavier elements. The sun's core is where nuclear fusion occurs. At a temperature of about 15 million Kelvin and pressure of 250 billion atmospheres, hydrogen nuclei fuse into helium. 4 hydrogen nuclei combine to form 1 helium nucleus plus energy. This is the proton-proton chain reaction, the dominant fusion process in the sun day. Each fusion reaction releases about 26 MeV of energy. Doesn't sound like much, but the sun fuses about 620 million tons of hydrogen every second. That's enormous. The energy released is what makes the sun shine. Radiant energy, light and heat. This energy takes about 100,000 years to travel from the core to the surface. Photons are constantly absorbed and re-emitted by atoms in the sun's interior, bouncing around. Random walk. Eventually, they reach the surface and escape as sunlight. That sunlight takes 8 minutes to reach Earth. It powers photosynthesis, drives weather, makes life possible. But fusion has a consequence. Every second, 620 million tons of hydrogen becomes 616 million tons of helium. 4 million tons of mass is converted to energy. E equals mc squared. This is the source of the sun's power, and it's unsustainable. Eventually, the hydrogen runs out. Now, the sun has enough hydrogen to last about 10 billion years total. We're halfway through. 5 billion years in. 5 billion to go. But the sun is not constant during this time. It's changing, getting brighter. Why? Because as hydrogen fuses into helium in the core, the helium accumulates. Helium is heavier than hydrogen. It sinks. The core becomes more helium-rich. And helium doesn't fuse at these temperatures and pressures. It's inert, just sitting there. This means the core contracts slightly, gets denser, hotter, and the fusion rate increases, more hydrogen fuses, the sun gets brighter. This is a gradual process. The sun's luminosity increases by about 10% every billion years. Over the sun's lifetime, its luminosity will roughly double. It's already about 30% brighter than when it formed 4.6 billion years ago, and it will continue brightening. In about 1 billion years, the sun will be about 10% brighter than now. That doesn't sound like much, but it's catastrophic for Earth. Earth's climate is finely balanced. A small change in solar input has huge effects. When the sun is 10% brighter, Earth receives more radiation. The temperature rises. water evaporates. Water vapor is a greenhouse gas. More water vapor means more warming. This creates a feedback loop. More warming, more evaporation, more greenhouse effect, more warming. Runaway greenhouse effect. The oceans boil. Water vapor is lost to space, split by UV radiation into hydrogen and oxygen. Hydrogen escapes Earth's gravity. Oxygen reacts with surface rocks. Earth's water is gone. The atmosphere thickens with CO2 from volcanic outgassing. Surface temperatures rise to hundreds of degrees. Earth becomes Venus, a dead world. This is the fate of Earth in about 1 billion years. Not 5 billion, 1 billion. Long before the sun becomes a red giant, life on Earth has 1 billion years left. Maybe less if we accelerate warming through greenhouse gas emissions. But even if we solve climate change, even if we stabilize the current climate, we can't stop the sun from brightening. It's a consequence of stellar evolution, inevitable. Now let's talk about what happens in 5 billion years. When the sun exhausts the hydrogen in its core, the core stops fusing. It's now mostly helium, inert. The energy production stops, but the outer layers of the sun are still massive. They press down on the core contracts under gravity, gets hotter. Eventually, the temperature at the core's edge reaches 15 million Kelvin. Hydrogen just outside the core starts fusing. This is shell burning. Hydrogen fusion in a shell around the inert helium core. Shell burning is unstable. The shell produces enormous energy, more than core fusion did. The sun's outer layers are pushed outward. The sun expands dramatically. The surface moves farther from the core and farther from the heat source. The surface cools. From 5,800 Kelvin to about 3,000 Kelvin, the sun becomes redder. Cooler surface, but much larger. This is the red giant phase. The sun will expand to about 250 times its current size. Its radius will reach about 1 AU, 1 astronomical unit. The current distance from the sun to Earth, the sun will engulf Mercury's orbit. It will engulf Venus's orbit, and it might engulf Earth's orbit. Will Earth be swallowed? This depends on several factors. As the sun loses mass through stellar wind, its gravitational pull weakens. Earth's orbit will expand slightly, maybe enough to avoid being engulfed. Current models suggest Earth will just barely escape, orbiting at the edge of the sun's atmosphere. But even if Earth survives physically, it won't survive thermally. The sun's luminosity during the red giant phase will be about 2,000 times current levels. Earth will be heated to temperatures of 1,000 Kelvin or more, hot enough to melt rock. The surface will be molten. Any remaining atmosphere will be stripped by the intense solar wind. Earth will be a ball of magma, dead, sterile, uninhabitable. Nothing will survive. Even if Earth escapes engulfment, it will be destroyed. Now, the red giant phase doesn't last forever. After about 1 billion years, the helium in the core reaches 100 million Kelvin, hot enough for helium fusion. 3 helium nuclei fuse into carbon. This is the triple alpha process. The core ignites. Helium flashes. For a few minutes, the core produces enormous energy. The sun stabilizes. Now it's fusing helium in the core and hydrogen in a shell. This is a brief, stable phase, lasting only about 100 million years. Then the helium in the core runs out. The core is now carbon and oxygen inert. The sun enters a second red giant phase, helium shell burning. The sun expands again, becomes even larger, more luminous, more unstable. During this phase, the sun will undergo thermal pulses, instabilities in the helium shell, periodic bursts of fusion. Each pulse ejects material from the sun's outer layers. Stellar wind becomes a gale. The sun loses mass rapidly. About half its mass is expelled over a few 100,000 years. This expelled material forms a planetary nebula, a glowing shell of gas expanding around the sunday. And at the center, the core remains, a hot, dense remnant about the size of Earth, but with half the sun's original mass. This is a white dwarf. The sun's final form, the white dwarf will shine for trillions of years, slowly cooling, radiating its residual heat into space. Eventually, it will cool completely, becoming a black dwarf, a cold, dark cinder. But this takes longer than the current age of the universe. For trillions of years, the white dwarf will be visible, a faint ember of what once was a star. And Earth? By the time the sun becomes a white dwarf, Earth will be a frozen, airless rock orbiting far from the dying star. No light, no heat, no life. Frozen solid, dead for billions of years. This is the fate of our planet, written in the physics of stellar evolution, unavoidable, certain. Now let me address some common misconceptions. Can we save Earth? Can we move Earth's orbit? Theoretically, yes. If you could apply a continuous thrust to Earth, you could gradually push it outward. Keep it in the habitable zone as the sun brightens, but the energy required is astronomical. To move Earth significantly over 1 billion years requires changing its orbital velocity by kilometers per second. The kinetic energy involved is about 10 to the 33 joules. That's 1 billion times more than all human energy consumption in history. We'd need to harness the output of the entire sun for years just to move Earth slightly. It's technically possible, but practically impossible with any conceivable technology. Another idea is to use gravitational assists. Repeatedly swing asteroids past Earth. Each flyby transfers a tiny bit of momentum. Over millions of years, you could shift Earth's orbit. But you'd need billions of flybys. Coordinating this is beyond our capability, and one mistake, one miscalculation, and you crash an asteroid into Earth. Extinction event. Not a good strategy. Could we build megastructures? A Dyson sphere to capture solar energy and use it to move Earth? Again, theoretically possible. But building a Dyson sphere requires disassembling planets, mining asteroids and planets for raw materials, constructing structures on the scale of orbits. Civilizations that can do this are Type 2 on the Kardashev scale, harnessing the entire output of a star. We're Type 0.7. We're not even close. And even if we built a Dyson sphere, the sun will still evolve, still become a red giant. The sphere would be destroyed or need to be moved outward as well. It doesn't solve the fundamental problem. The sun is dying. You can't stop stellar evolution. Could we leave Earth? Yes. This is the only realistic option. If humanity survives long enough, we'll need to leave. Not just Earth, but the solar system. Find another star, another planet. Terraform Mars temporarily. But Mars will die too when the sun becomes a red giant. We need interstellar travel. As I've discussed before, interstellar travel is incredibly difficult, but it's possible in principle. Generation ships, sleeper ships. If humanity lasts 1 billion years, we'll have that technology. We'll leave Earth and find a new home, or we won't, and we'll die with our planet. Now let me talk about other stars. The sun's fate is typical for stars of its mass. About 90% of stars are smaller than the Sunday red dwarfs. These stars live much longer, trillions of years. They burn hydrogen slowly, efficiently. They never become red giants. They just gradually fade. Planets orbiting red dwarfs could be habitable for trillions of years. Much longer than planets around sun-like stars. But red dwarfs are dim. Habitable zones are close to the star. Planets are tidally locked. One side always faces the star. This creates challenges for habitability. Hot side, cold side, extreme weather, but maybe life adapts. On the other hand, stars more massive than the sun die much faster. A star twice the sun's mass lives only about 1 billion years. A star 10 times the sun's mass lives only 20 million years. These stars become supergiants, much larger than red giants. They explode as supernovae, destroying everything nearby. Planets around massive stars have no chance. The star dies before complex life evolves. Only stars like the sun or smaller give life enough time, and even then, it's temporary. Eventually, all stars die, all planets die. This is the fate of the universe. Let me tell you about the distant future. In about 100 trillion years, star formation will cease. The gas clouds that form stars will be exhausted. The last stars will be born, small red dwarfs. They'll burn for trillions of years, but eventually, even they will die. The universe will enter the degenerate era. No stars, just stellar remnants, white dwarfs, neutron stars, black holes, and cold planets drifting in the dark. The universe will be dark, cold, dead. This is the ultimate fate. Heat death, maximum entropy, no energy gradients, no stars, no life, just a uniform, cold, empty universe. And this fate is guaranteed by thermodynamics. The second law, entropy always increases. Stars burn hydrogen. Convert low entropy nuclear fuel into high entropy radiation. Increase entropy. Eventually, all free energy is used up, all stars die, the universe reaches maximum entropy, heat death, nothing can stop it. This is the fate of the Sunday, the fate of Earth, the fate of all stars and planets, temporary structures in a universe running down. Now let me address why this matters. Why should you care about the death of the sun billions of years from now? You won't be alive, humanity might not exist, Earth might be abandoned long before then. True. But understanding the sun's fate is understanding our place in the cosmos. We are temporary. Our planet is temporary. Our star is temporary. Everything is temporary. The universe is not static. It's evolving. Stars are born and die. Galaxies collide and merge. The universe expands and cools. We exist in a brief window, a moment of cosmic history when stars shine and planets exist. This window will close, not in our lifetimes, but eventually. And this perspective, this cosmic perspective, is humbling. We are small, temporary, fragile. Our existence depends on a star that is dying, slowly but inevitably, and there's nothing we can do about it except appreciate the time we have. After 50 years of studying physics, I've come to see humanity's fate as tied to cosmology. We exist because of stellar processes. The sun formed from a collapsing gas cloud enriched by previous generations of stars. Those stars fused hydrogen into helium, helium into carbon, oxygen, and heavier elements. They died in supernovae, scattering those elements into space. The sun formed from this enriched material, and so did Earth. Every atom in your body was forged in a star. You are star stuff. And you exist because stars die. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all came from dying stars, supernovae, red giants, planetary nebulae. Stars create the elements, and stars destroy the planets. This is the cycle. Creation and destruction, and we are part of it. The sun will destroy Earth. Not as punishment, not as tragedy, just as physics. Stellar evolution, the laws of thermodynamics, the inevitable increase of entropy, The sun is burning through its fuel, and when the fuel runs out, the sun will swell, brighten, and die, taking Earth with it. This is not a maybe. This is a certainty. Written in the equations of stellar structure, the sun has been shining for 4.6 billion years. It will shine for 5 billion more. But it's not eternal. Nothing is. And understanding this, accepting this, gives us perspective. We are here now. We exist now. We have this moment. And we should make the most of it, because the sun is dying. And one day, so will we. Thank you for watching. Now you know why the sun will destroy the Earth. Welcome to Stellar Evolution.